Good afternoon. Hopefully you're all here, so many of you, because you're web developers, you're confident making stuff on the internet, you're confident writing HTML and CSS and JavaScript, but you don't know how to build hardware. You don't understand how these gadgets that people talk about that we're building on top of work. In this talk, I want to show you how to take your skills, how to use the stuff you already know, how to extend this a little further to actually be able to write code that interacts with the real world, to write code that makes changes, lights up LEDs, and so on, that reads inputs from the real world. And we're going to do this through a series of live demos. There's going to be quite a bit of live coding and some live electronics here. I do want to warn people up front that these, of course, are going to go horribly wrong at some point. Something will blow up in my face. But we do have a workshop after this at 3:15 in the Taipei room, straight across. So you can come and have a look there, and I'm going to have all the hardware here and a bit more so that you can come and play around with it yourself, take a closer look at these demos, and try and work out why everything has exploded. So, to get started, I'd like to just dive in, but unfortunately, I don't actually have a slide clicker. So the first thing we're going to do is build one of those from scratch. This is a MetaWare C. It's a tiny little board that has a Bluetooth microcontroller on it, so exposes everything on it over Bluetooth, and there's some standard firmware that comes with this, and has a bunch of sensors and things we'll talk about in a minute, and critically, a button. And this is powered with this tiny little watch battery. And this is a quite impressive device. On just that watch battery, it will last for absolutely ages, and it comes with good libraries for connecting to it and automating it with anything else, like JavaScript. So I'm going to write some code that runs on my laptop, connects this, and uses it to control my laptop. To do that, first, we need to actually find the device. So it exposes itself over Bluetooth, and we hunt this down and connect to it. And we want to do something like this, and print once we pick up a MetaWare device nearby. And then we want to do connect and setup, and wait for that device to actually connect to us and start offering an API to read everything that's going on here. We need to do a standard bit of Node stuff here. So this is just a Node script to watch out for errors. Oh no, something went wrong, and return if that happens. But if it doesn't, we're now connected to this device. Ooh, interesting. Yeah, okay, we can definitely do that. Who can remember how preferences works in Visual Code? Something like this. How does that look? Bit more readable? Can you see that at the back? Yeah, some confident nods. Great. OK, so we've imported two Node modules, Node MetaWare, which is the library for this, and Robot.js, which I'm going to use to control my computer. We've found the MetaWare device. We've connected to it at this stage. And we now need to get hold of the button itself. So we have to use this slightly weird API here, where we pass device to device. This gives us the button. We register for events. Say button.onChange. So if somebody's pressed the button, let me know. And then in here, we can do anything we like. And at this point, we've got JavaScript that is listening to events happening on a remote device. You can write this out in, what, a minute? And all of a sudden, now you can write JavaScript that starts to interact with the real world in a very simple way with buttons here, but we can take this further. Let's get this working first. So if that button's been pressed, then we're going to go robot key tap. And we're just going to press right. So if I press this button, flick to the next slide through my presentation, and I'm just going to make this slightly more reliable because I need this to actually work for the rest of this talk so that I can show you the rest of the slides. So let's do this. If we get an error, actually just retry. And if at any point we get disconnected, then, well, let's just try again, shall we? So it's a relatively simple Node script that should give us a working clicker. Oh, and the one other useful thing is to know once it's actually connected. Great. So here we have slide clicker. Let's run it. It should, after a couple of seconds, over Bluetooth here, oh, we might be a bit far away. Let's move this up here. Find that device. It'll then connect to it any second now. There we go. And just like that, I should now be able to click through my slides. This is pretty cool, right? Do you remember that first time as a web developer you ever built a web page? When you first wrote out some HTML, some huge bright red text, "I am the best programmer ever." That's a satisfying, magical moment. That is a very cool and exciting thing to be able to do. All of a sudden, the web, this broad network of sites that we're all using and looking at and engaging with every day, is no longer something distant, built by somebody else, but something that you can build yourself, something you can understand, and something you can change. You can get that same magic with hardware. It's not as difficult as you'd imagine, and you can buy simple, off-the-shelf components, write some simple JavaScript, connect to them, and do useful, interesting things. This device itself is a MetaWare C. They sell, I think, for about $40 or $50, so it's a little bit expensive. There are cheaper things in the same kind of market. I think Texas Instruments make a sensor tag. So it's in the same sort of ballpark. It's a remote sensor. It runs a microcontroller, and you could put firmware on it, but it's not really designed to do that. It's designed to just expose what's on here to be controlled by somebody else. And on here, you have a lot of things you can use. We've got Bluetooth, of course, but we've also got this button and then an accelerometer, so we can tell how this device is moving around. We've got a gyroscope, so we can pick up rotation. We've got temperature sensors, so we can read environmental data out of here. And GPIO. These orange circles are general-purpose input-output that allow us to connect other bits of hardware, and you can extend this further if you want to. This alone lets you start interacting with the real world. And there's loads of interesting ideas for stuff we can do with this kind of thing. Firstly, we can, for example, start just monitoring the things you use every day. You can stick one of these to your seat, and all of a sudden, your computer can know whether you're sat down or not. You can set up your laptop to lock every time you stand up and leave your desk. You can really easily just start integrating this sensing. You can, if you're feeling quite keen, build a minimal smartwatch out of this. Stick a strap and a support on it, maybe, I don't know, add a buzzer, that kind of thing. And you can remotely push notifications to that from your laptop or from Android. There's an Android library as well, and iOS, I think. So you can really easily start extending this out. And there's a actually quite passionate DIY smartwatch community using devices like this to build their own gear. And similarly, you can take this and you can build intelligent beacons. You can just add little Bluetooth devices around you and start picking up information from the environment. You can put one on your desk at work and one at home and have your laptop open your email when you arrive to work automatically and turn off all notifications if you open it at home. So we can get a lot of interesting potential and power just out of quite simple, basic devices like this. We don't have a lot of control here, though. This is a very good way to get started and lets you very quickly build interesting devices. But if you want to go further, you need to actually start looking, most of the time, into the lower level electronics. And the best way to get started with that, I think, is an Arduino. So this is the Arduino Uno. It's again, simple microcontroller device, but here set up much more to encourage you to directly control what's going on. The main interesting part of this is that large black block. That is the microcontroller here and runs the entire platform. It's a simple, very stupid processor. So it's an 8-bit processor. It's got a couple, maybe 2 kilobytes of RAM, that kind of ballpark. So very, very low powered and very simple. But because of that, if you want to integrate with the hardware around it, it means there's no distractions. There's no real complexity here. You can directly write to the hardware. You don't have to worry about an operating system or anything like that. You write code. Traditionally, you write code in C. You upload it to this. It runs on that processor directly, does some things, and that's it. There's nothing else going on. We obviously don't want to be writing C here, but we'll get to that in a sec. The interesting other part of this is the pins down the side. If we rotate this, you can take a bit more of a look. These give us interactivity. These let us connect to other hardware devices to start building circuits and more complicated structures. So we've got a few different types of pins here, and this is similar on many other devices if you want to do low-level electronics. They're all going to have the same kind of pins and the same sort of structure. First, we've got power pins down the side. So these give us 3.3 volts and 5 volts out from 2 of these pins. So it's just constant voltage all the time. And then there's 2 ground pins that we can close our circuit with. We've also got analog read pins. So here, if you send a voltage to this pin, on the chip, you can read that voltage. So you can read a changing analog voltage, perhaps a temperature from a temperature sensor. And finally, over here, we've got digital read and write pins. So these let you read a high and a low voltage, but not really judge the points between, and also write a high and a low voltage. And there's also some of these that have tildes, which is probably not visible on this screen. I will put these slides out on Twitter later so you can have a closer look. Some of these, though, a few, are not only digital write, but are also analog write. This uses something called PWM, pulse width modulation. So these pins can't actually write a varying voltage between places, but they can very quickly change between low and high voltages. So analog writing, generally with boards like this, is actually flicking very quickly between high and low. And if you do that half the time, it's about the same for most hardware as having a constant average voltage. So with all of this, we can start building circuits. We need a way to connect this together first, though. If you're not familiar with electronics, you will have seen breadboards quite a lot, but not really understood what's going on. They can be sort of opaque if you don't really understand. Underneath the hood, they're actually fairly simple. What's happening here is that these pins are connected together and act as a base that we can put components in to start building circuits without having a mess of loose wires. So internally to this, actually they're wired up like so. We've typically got 2 rails on the top and bottom that by convention we use for power and ground, and a bunch of connections between the rows of 5 pins all the way through so that we can start clicking things in here and building circuits in place. Let's try an actual circuit with this. This is probably the simplest circuit you're going to see. If I break this out, ooh. There we go. You should be able to. Let's just do that bigger, in fact. Yeah. Great. So here you can see the Arduino. So this is the live circuit I'm building here. Is this screen good enough that I can do that and you can see what's going on? It's OK. We can swap back and forth. So we want to build this circuit in this Arduino. It's going to be fairly easy to do. We need to set up a resistor that comes from the power and goes to one of these rows, just like that. And you need the resistor here because of how LEDs work. So an LED can only support a certain amount of current, a certain number of amps. And if you put too many amps through, you'll kill the LED. You break it. I don't want to get into the theory of electronics particularly, but the current is controlled by the voltage. If we add more by the resistance. If we add more resistance with a constant voltage, we lower the current in the LED so that we don't break it. So you need to have the resistor in here to make this work. We then connect the 5-volt pin to the breadboard. Let's take a look at that. And then, hopefully, connect the ground here to the ground over here. And just like that, the LED lights up. So with this, we can do some fairly basic, easy electronics. And this very quickly lets you start building simple electrical circuits. And if that's what you want to do, this is a great start. And there's lots of interesting things you can do with electronics. You can get quite deep into this and start building electrical machines. But I'm not really interested in that. What I'd like to be able to do, and what I suspect we'd all like to be able to do, is control this with JavaScript. So instead, we need some kind of circuit that's programmable. Fortunately, this is a pretty easy change here. We just have to move from that constant 5-volt pin across to one of these digital write pins on the other side. And then we're going to write a constant or changing voltage to that we can control from JavaScript. So the actual circuitry for this is very easy. We move that to here, So that's pin 8 down the side there. And then we need some way to actually write a script that manages this. So to do that, generally you're going to use a library called Johnny5. Johnny5 supports this Arduino and actually a whole load of other boards. If you're doing anything like this, generally you want to be using Johnny5. It's very reliable. It covers all of these things very well. It's got built-in support for lots of components and makes it very easy to get set up. Because it's so popular, also almost every JavaScript tutorial you see doing this kind of thing will be using exactly the same library. To actually do this then, in this circuit, we need some way to control this. And that's going to be over here. We see that? Yeah. So I've imported two libraries here. One is Johnny5, and the other is a library called Temporal. This gives you things that you basically already have with set timeout and set interval, so it's just managing, scheduling events, but does it in a slightly different way. Johnny5, a lot of the community around Johnny5 is looking more at robotics and controlling actual motors and more complex electronics. And if you start getting into that, timing becomes quite important. And Temporal internally is actually using set immediate to run constantly and manage timing itself so that it can be more precise about the prioritization and about exactly which events are going to happen when. In practice, you can ignore this. Just as a rule, if you want to be doing anything with timing in electronics, in JavaScript, like here, you want to be using Temporal rather than set timeout. So to actually control this, we need to go like this. So we're not putting JavaScript directly on this chip. As I was saying at the beginning, it's a tiny chip. It's an 8-bit processor. It's got nearly no RAM. You're not going to run a JavaScript runtime on this. Fortunately, though, it comes with some standard firmware that exposes everything that you'd normally have if you're running on the device over USB. So Johnny5 connects to this firmware and does essentially the same thing you write in C, but remotely from this laptop, and allows me to write code to do that without having to worry about trying to do so in the constrained, limited environment we've got on this board. But that does mean we have to wait until we've connected to it here, and then we're going to push commands to that. What we want to do first is start writing to that pin. So we need a new pin, and this is going to be pin 8. That's the pin I've connected down here. And let me just set pin.high. If we go back over here, and I run index.js, you can see it connects to it, and then down in the corner, the light turns on. Just like that. You can write JavaScript that controls low-level electronics. We can do more complicated things from this. So let's try using Temporal and make this like blink. This is almost the hello world of low-level electrical programming here. So what we're going to do here is set it high every 1,000 milliseconds and every 500 milliseconds, so alternating between these two, set it low again. There's nicer ways to do this in Temporal, but they're slightly more complicated to write out, so I'm going to ignore them completely. This, again, is going to connect, and now, unless I've done something wrong, that LED should start blinking on and off. And now you can write JavaScript that not only talks to small remote devices, but directly writes voltages to pins and starts powering and controlling electronics. Again, this is pretty easy. I can do this electronics for you live on camera. I can write all the code in a couple of minutes, and you can immediately start getting going with this. More interesting, probably, is being able to read things back into your JavaScript from the real world. So to do this, we're going to need some kind of components. We're going to start here with a potentiometer, which looks something like this. Hopefully that's visible. Yeah, so this is a small dial that I can turn, and that controls the voltage that comes out of this. This component has 3 pins: power in, another pin that goes down to ground, and input-output. So we run a current across these, and then we can read a voltage from this 3rd pin. So let's do that now. Firstly, let me kill Johnny5. And then let's bring that back up here. So we don't want any of this anymore. What we're going to need is a constant voltage through here. Let's set that up there. And some current that goes through this potentiometer and then actually reads the result. So firstly, let's set up some current through here. So we put some power in there and some power out over here. Let's see if I can, oh, let's not do that. See if I can set that up there. Great, so we've got that coming in through here. And then we connect up pin A0. So this is one of these analog read pins that can read a varying voltage. So there we've got essentially the same circuit as you've got on that slide there. Let's see if I can make this a little bit bigger. And now we've got a varying voltage coming into that A0 pin. So if we can read that, we can tell where this dial is set. This is actually even easier than what we were doing before. So we write A0, and then we say pin.query. We get the state, and we log the value. And what we're actually going to do is do this in a loop, just so we can monitor it as it goes. So we get the analog pin, and we read it every 500 milliseconds, and we see what values we get back. Let's take a look at this. So if we spin that up, that should now start coming back with whatever this potentiometer is currently set to. So it's currently at 611. If I turn this all the way, you'll see that goes up to 1023, and I can turn it back down, and it'll drop back down to 0. So now we're reading out from low-level electronics, and you can immediately, if I don't pull this circuit apart, the downside of breadboards, you can immediately start using this to interact in interesting ways. Straight away from this, if I wanted, I could set this up as a volume control for my laptop. That's quite easy to do from the JavaScript side. Robot.js has things to simulate keyboard events, for example, so you can simulate volume up and down, or you can integrate with whatever on the system you like. And immediately you've added an extra control to your computer. You can add extra buttons, you can add extra inputs. Quite a lot of other inputs can be slightly more complicated here. So the potentiometer internally is doing something for us called voltage division. This is a voltage divider. If you want to read lots of other components, you have to do that yourself. So many things you will have seen, such as this. Is that visible? Maybe? This camera doesn't really like focusing. Okay, so this is a light resistor. So this changes its resistance based on the amount of light that is coming in. Unfortunately, we can't directly measure resistance. What you get on these pins is the ability to measure voltage. Again, I don't want to spend lots of time getting into the theory of circuitry, but what this means in practice is that you need to set up a slightly more complicated circuit. And that looks like this. So firstly, we have to have the power coming out and going through the resistor. So we're going to take that power out here, and I'm going to put that in over here. Once you've got that power out, you then, I think that should work. Once you've got that power out, you then have to split the circuit. One route of the circuit goes through a constant resistor into the ground. So let's set that up here. And the other route of the circuit goes back into the analog in. This means that, so the way that voltage comes through here is based on the ratio of the two resistors. So this allows us to change the resistance of this light resistor and have the voltage change that we're going to start reading. So currently you can see we're getting 125, 123, and if I cover this up now, that goes down to 40 or so, 30. So we can now read from light sensors like this. The actual range here is more limited than what the pin can support. So if you saw the potentiometer, that was going from 0 to 124. That depends on the strength of the other resistor you use here. So So if you want to change that range, you can change this resistor to manage what you get through. But already we can see that we can tell the difference between low and high light situations. Okay. This is a fairly basic intro to electronics. It's a large topic. If you do want to get started, there are loads of quite good resources for this. One of them is the Arduino Starter Kit. So I've actually got one of these here with me, so you can come and have a look at it in the workshop if you like. This is the standard kit. It's very good. It has everything you might need. It does focus on the C side, though. Most of the examples you can translate fairly directly into Johnny 5, but it's worth watching out for. If you'd prefer to look on the Node side, there's a great project, nodeardx.org, the Node Arduino Experimenters Guide, I think that stands for, which is detailed node examples to start getting involved with bigger and bigger circuits. And the next sort of levels up from here are starting to look at motors and things, which are slightly more complicated, but really just small steps along the same kind of path, and building up larger circuits as you connect these together. Hackster.io is another pretty good example. If you've never seen it, it's a huge collection of published projects by various people working on this kind of hardware, writing up all the hardware they use to build it, the setup instructions, providing all the code and so on, and finding other simple projects on there, trying to work out how they work and build them yourself is another pretty good way of getting into this. And generally just trying to actually build something, picking this up, getting started, and trying to work out how circuits work by trial and error is remarkably effective. Some things are breakable, so if you put too much current through an LED, you will break it, but these cost cents. They're incredibly cheap. It doesn't really matter if you blow them up. It's quite easy to replace and manage this stuff and see what happens. Okay, what can we actually do with this? You now know everything about electronics. Where can we take this? Quite an interesting, good example is a light alarm. So I've heard lots of people talking about these recently as instead of having an alarm clock in your house that goes off very loudly, having a bunch of LEDs that sits above your bed that slowly gets incredibly bright so that you wake up slightly more naturally is apparently quite nice, and it certainly sounds like a much better way of getting up, and is quite easy to do with this level of electronics. Plant waterers are a pretty classic Arduino project. You can get resistors that are based on the, what do you call it? Humidity, based on the humidity, and these plug into soil, and then you connect them up and do the voltage divider as here. And you can immediately start telling when your plants are getting dry, and then connect up a pump to that and power the pump to start watering them when required. I think one of my favorites from here is the Inbox 0 button. This is a project somebody's actually done up on GitHub there. It's a fairly simple circuit. It's slightly more complicated than what we've got here, and it adds a switch, but it's essentially the same, powered by Johnny 5. What actually happens here is that you authenticate it with Google, you press the button, and that first yellow light starts blinking, and then the second yellow light starts blinking, and then the third yellow light starts blinking, and then it deletes all your unread emails. Okay, so all of this is pretty fun, and you can start actually building real electronics. You can feel like this powerful electrical genius who can make lights turn on and off at their whim. You probably want to go a bit bigger than that. It's good to understand this if you want to integrate with arbitrary components, but a lot of the time you'd like to have stuff just work. And this is where Raspberry Pis come in. Almost everybody has probably heard of the Raspberry Pi at some point. They're a great platform. They're quite a bit more complicated than an Arduino, but in return for that, they give you a lot more power. So this has an ARM processor that is an actual substantial processor you can run a real operating system on. So you can run Linux on these devices. It's got an SD card slot, so you're going to give it a real hard drive with substantial storage. It's got 4 USBs. It's got Wi-Fi. It's got Bluetooth. It's got a network socket. It's got HDMI and audio out. You've got serial connectors for displays as well as HDMI. serial connectors for cameras, and also 40 GPIO pins, so we can do manual electronics on that, as with the Arduino. This gives you a lot of potential power and is almost a little bit intimidating. There's a huge amount we can do with this. To start with right now, I've got a project set up here, running 3 webcams on these 3 Raspberry Pis around here. And each of these are just streaming video out to anybody who connects to them. So let's actually take a look at this. This is the bit where we check whether the Wi-Fi is working. Let's try that one, for example. And just like this, you can see that's probably this video here. So you can see yourselves on camera. How exciting. We can also do, what are the other ones? 150, this might be me. No, that's the other one pointing at you lot. And we've got 237 over here. And that one is going to be my elbow. Yes, great. So we've got 3 simple Raspberry Pis here running webcams. So these themselves, as standalone devices, can stream video out. And you can connect to them and watch whatever's going on. And these will happily let as many people as they like join them, and you can refresh. And the video will, after a little bit of awkwardness, resume, and so on and so on. So these are pretty neat bits of kit. The actual hardware for setting this up is pretty simple. Let me just kill that. So if we take a look at this, it's just that camera there connected to a Pi and to USB, and that's running over the Wi-Fi. The actual code for this as well is not too bad. So we've got this over here. We do a little bit of node setup just to catch any errors and log them so that I can work out what goes wrong in a minute. We've got Express here. So if you're not familiar with this, this is a Node web server. It's very simple and easy to use, similar to Sinatra, if you've used that in the Ruby world. And RaspbiVid Stream. RaspbiVid is a library and a tool that come from the Raspberry Pi Foundation for using exactly these cameras. And the RaspbiVid Stream is a library I've made that just wraps these and chunks the frames so that you can stream them out to a client, and it will happily render them. I'm not going to go into that right now, but it's about 100 lines. It's not very complicated. I can show you in the workshop if you like. We set up the app. We add ExpressWS, which gives us WebSockets in the app so that we can stream content rather than just doing request response. And if we get an HTTP request for the root of the site, we serve index.html, which is even simpler than this, and just loads this H.264 client-side video player here. So this is based on Broadway, which people might be familiar with, client-side. It's a JavaScript video decoder for H.264, and some things to glue it together to Canvas. And then here we say, here's a canvas, make me a video player, connect it to this server /video stream. And that will start requesting the video stream and playing it on the canvas. And the actual video stream itself is where kind of the magic happens here. So if you ask for a WebSocket from this server, you connect, it sends some initial config. This is the size of video we're going to be sending. And then it gets a stream of the video from the device itself, which it flips because these cameras are actually upside down. We then, every time we get a frame of video through, we pass it to the WebSocket. And when you close, we stop sending you video. So that's the whole thing. There's a little bit more down at the bottom that just does some more error handling and actually starts the server. But that's all the logic you need to build webcams with a Raspberry Pi. Because we can run code directly on these devices, because they're real Linux devices, because they are powerful enough to decode video and to easily use tools that we already know to run a server, you get a lot more power here. Doing this on an Arduino is very complicated, if not impossible. Doing this on a Raspberry Pi is under 100 lines. Okay, what we'd probably like to do, though, is extend this a bit further. So we've got these 3 Raspberry Pis. We'd like to do some more actual electronics with this. Let's make something a bit more interesting. There's all sorts of stuff you can do. Again, we've got GPIO pins, as with the Arduino, so we could wire up all sorts of interesting goodies. You can set up a buzzer, for example, every time somebody looks at the webcam. You could set up a little robot arm and put controls on the webcam website so that you can move it around. this sort of thing. You could set up some sort of counter that shows how many people are currently on the webcam, and hook that up to the device. Doing all of this electronics is interesting, but relatively complicated. And what we'd actually probably like to do is have something that just works. And because of this, there are a lot of hats. Hats are a standard from the Raspberry Pi Foundation for pre-built bits of electronics that come with 40-pin connectors, so exactly fit on the GPIO of a Raspberry Pi, and don't require any circuitry. Sets of components pre-wired together, hooked up to the right pins that just click on top without you having to do the wiring. So a quite nice example is the Enviro P hat, which I actually have one of here. This is a tiny little bit of equipment that comes with a connector to just click onto a Raspberry Pi. And if you click it onto a Raspberry Pi, gives you, pre-wired and set up, a motion sensor, so you've got gyroscope and accelerometer, light and color sensors, and some LEDs, and a barometer, and a temperature sensor, and so on, without having to do any wiring. This is technically a P hat, because it's a partial hat, mostly because it's smaller than a full hat, which is normally the size of a Raspberry Pi. But this really easily lets you integrate with these components. There's lots of almost click-together electronics you can do with Raspberry Pis because they're such a popular standard. And there's lots of other devices now that use the same GPIO layout because it's so easy to build and connect together devices like this. The one I want to look at, though, is Blinked. Blinked is the tiniest hat you can imagine. It consists of 8 LEDs, and that's it. It provides these 8 little LEDs, each of which are RGB controllable, so we can set the colors of these and the brightness of these totally independently, and which don't require any wiring or setup. You take this 40-pin connector and you attach it to a Pi. Let's do that. So, take the 40-pin connector and you attach it. Ooh. You attach it to a Pi. Click. Just like that, you've got LEDs that you can now access from the Pi itself. This is probably the easiest electronics you will ever see. If we want to actually build with this, we're going to need to do a little more. So, let's start doing some development on the Pi. Firstly, we need to get hold of Blinked. So, there's a node library for this, as there is for everything else in the world, and we just need to import that and make a new Blinked. Once we've done that, we then want to set it up, and we're going to need to do something with these LEDs. Let's light them up. So we're going to set them all to white, maximum brightness, and then we have to call send update to actually trigger the update on this. This is going to mean as soon as the server starts, all of these LEDs light up. We then also want to probably turn these off, because this is going to be quite bright. So let's go like this, and after 1 second, we'll say clear all, and we'll send an update there. But you can see this, as an API, is pretty readable, pretty understandable, I think, even if you've never seen it before. We now have to actually put the code on the Raspberry Pi. Arduinos have an advantage in that they don't have an operating system. They don't have anything else going on. They're incredibly simple. You just send the code over a USB or serial in some other way. For Raspberry Pis, that's not the case. It's a full operating system, and you get quite a lot of the complexity you get from managing a normal server. How do you deploy code to a server is an open, interesting question with a bunch of different answers. So you can set up your Raspberry Pi with SSH or with an FTP server and do that yourself if you'd like, and copy your things across. What I'm going to be using here is some of our infrastructure at Resin to do resin sync. This is part of our command line tool, which just does an rsync directly onto the device. So just synchronizes the files directly to this. So if we actually run this, we're now in, let's go here. We've now got the PiCam, and if we run resin sync, this, again, fingers crossed, because this is going over the Wi-Fi, this is going to connect to the device, shut down the current application, synchronize all the code that we've just written onto that device. spin the current application back up, and hopefully the webcam should burst back into life, and the lights on these should jump up. I've actually just realized I might have done this wrong, because I don't know which one I'm syncing to, and only one of them has LEDs attached. Let's just quickly do that before it reboots. Perfect. Okay, so this is syncing across now, and now it's synced, so it's shutting down the current webcam, restarting it, and one of these is going to blink any second now, unless I've done it wrong, which could well happen. Drum roll. Oh no. Oh no. Well, that's annoying. Okay, that's not going to happen. Why has that not happened? Come, debug with me. Let's have a look. So, we can actually take a look at all these devices. This wasn't wholly the plan. Which device are we syncing with? 821. That's this one. LEDs.setTlePixel is not a function. That's because pixels are plural. Let's try that again. Okay, I still don't know which one of these devices that was either. I wonder if I can work that out. Oh, I can work that out. Let's simplify this. So if we get the IP of this, we can take a look. So, oh, and it's down because, of course, I've broken the code. So this is going to sync it across. So I'm afraid we'll have to wait another second there for this one to come back up to make sure these are nice and visible. And now the Wi-Fi's broken it. Okay, third time's the charm. There is no way that this could go wrong. Drum roll. I wonder if by breaking the device I've broken the Wi-Fi. I could switch to syncing a different one. Okay. So we're going to do a wonderful magic fix here, which is just to switch to the other one of the devices, because I think it's got upset there about that application crashing and stopping it syncing into the running container. It's lost connectivity there. So we're going to pick a different one of these, and one of these devices is now upset. Oh, although of course I could fix that. Let's do that by just rebooting it. Yeah. So over here now we should be syncing to one of these. This one definitely won't fail. And then once we've synced to that device instead should blink some lights into life. This all, again, is just going over rsync, which is a pretty good solution for this kind of stuff. Rsync isn't perfect, but allows you to get two folders working together fairly quickly. Hopefully now, surely, one of these is going to light up. Yeah, there we go. Success. Whew. Okay, so we can apparently put code on at least one device. It's probably interesting to do something slightly more complicated here, so let's try that, because that first one went so well. Let's try showing how many people are connected. So if we say clients equals, so we're going to get the WebSocket server, and we're going to get the number of clients we've got here, and then we're going to clear the LEDs. We're going to loop over these clients, and we're going to turn on LEDs for the ones that are actually there. So we'll do that. Let's make them red this time. And then we send update. So this gets the number of clients, clears all the LEDs, updates them to be the right number for the clients we've got, and then turns the LEDs on. And we need to actually do this whenever anybody joins or leaves. And also here. And we can also do this in here now to tidy that up a little bit. OK. So let's confidently sync to that one as well. So this should sync stuff across again. And then we can join the webcam, and we should start seeing more lights come up as I open more and more sessions into this webcam. While we wait for that, let's talk about how you'd actually deploy to more than one of these. So rsync works okay for synchronizing folders. If you want to just bring those together, that's all right, but that's not enough. Raspberry Pis are much more complicated to sync, potentially more complicated to sync to than simple servers. If you have any native modules, for example, in your NPM modules, those won't sync. This is an ARM processor. Yeah. That is a 64-bit x86 thing. Beep, beep, beep. And the compiled code on here won't run on that device. So you need to build your code on the device. And what we need to be able to do is push code here and then build an artifact over there. So there's a bunch of ways to do this. We do it with Docker, which is actually quite a nice solution for this. Who's familiar with Docker? Show of hands. OK, pretty good. I'm going to say maybe a third, maybe half. Docker's pretty good for a lot of things. You'd normally use it for managing servers. But for IoT, it actually works quite well. If you're not familiar with it, you can think of it as being like a virtual machine, but in a much more lightweight way. So you build an image which describes a bunch of files in an exact reproducible format. So the code of your project, also the NPM stuff that's installed, also your config files and the packages installed on the system. The whole thing. You build an image from, and you can then ship images around, and indeed ship diffs between images around. You can move these between devices, and you can start them up very quickly as a container. Very quickly is maybe a quarter of a second, something like this. So you can spin up this code, get things started, and you can then do a bunch of stuff with it, like rsync code into it. And at any point you like, kill it and restart it in well under a second, and get back to exactly where you were before. So for distributing reproducible images, Docker becomes a really good model. And this also works for IoT really nicely. Docker's quite lightweight, and it works pretty well. You need an operating system to support this. So we've made Resin OS. This is an open source free operating system. It's essentially a very lightweight Docker build with everything else stripped out that exposes all the interesting bits of the hardware into Docker. So you can control your network settings from inside your Docker container. You can talk to webcams, for example, from inside your Docker container. And you can do everything you'd want to be able to do on something like a Raspberry Pi. This is interesting, and using our tools there, so there's a command line tool that, again, is free and open source that comes with this. You can push code to the device, have Docker build your code on the device and build the image there and start that up. That works pretty well. If you want to distribute this to a bunch of devices, you need our main platform, which is Resin.io, which actually just takes this down to git push. This is what we're going to look at in a sec. So here what happens is we build this on our Docker servers in the cloud and then magically distribute it everywhere. So we should be able here now to add all of this. Let's call it magic. I think that's fixed, isn't it? Set all pixels. So it should be plural. Yeah, so it's set pixels singular when you're setting just one, but set pixels when you're setting all of them. It's like they're trying to catch you out. So let's go like that. Great. And now let's push this to Resin. And that's going to send this whole code base up. And then you'll see, much like Heroku, if you've used Heroku, an entire build. So we bundle this all up in something that will run directly on a Raspberry Pi and send it to all of these. You don't need to use Resin.io for this. You can just use Resin OS, which is all free, and do this on your own devices. But if you want it to magically go through the cloud and to get the wonderful unicorn, you have to go up through here. And then you can just push code straight to us. And what will actually happen now over here is that these will all independently start downloading diffs for the latest version of that. So if we go into one of these, we should be able to see this. That is going to be fascinatingly dependent on the Wi-Fi, so we'll see how this goes. But if we give it just a second, these should spin up. In the meantime, we can take a look at whether the code that I synced a minute ago actually works. So one of these, which one did I sync to? I thought it was that. Yeah, so there you can see a red light is turned on. And 2, and 3, and 4, and 5. So we can now build, with these LEDs, a very simple webcam counter. Is that visible from the back? Yeah, great. So we can keep track of how many people we've got here. One last extension I'd like to make to this is to actually be able to count more than 8 people. We've only got 8 LEDs here, which is pretty basic. And hopefully our webcam is going to be so famous that we might need 32 LEDs, 24 LEDs, more LEDs. So let's take a look at that. If we want to, so that one's now downloaded it, and these two should pick that up in just a second. If we want to take a look at that, it's going to look something like this. Let's say we'll choose which color we're going to do based on the modulus of these users. So we can rotate through colors as we get more users, and then we can use some magic little ES6 to do that and set that color. I think that looks probably about right. Anybody think this is going to go wrong? Confident nods from the back. Okay, let's try this as the one last step here. So, how do I want to do this? Yeah, let's just push the whole thing, not that. This commits. More magic. Push resin. So that's going to push out, and then in a minute, once this is up, all of these should now be running exactly the same image, exactly the same identical code, and we should be able to look at these and see all these LEDs light up. And we're not going to bother waiting for that, so let's wrap up and we can come and take a look at the end. All of this is pretty neat. Raspberry Pis add some complexity to Arduinos. You need some kind of deployment setup to manage these nicely, especially if you want to have a bunch of them connected to Wi-Fi all over the world. But they let you do some really nice things. You can set up webcams remarkably easily, especially if you want to do sound or video. Arduinos become quite complicated. And here you just get things like Ethernet and Wi-Fi and Bluetooth straight out of the box. We can build some cool stuff. Digital photo frames are quite a good, interesting candidate. I've actually got one of these here, so you can come and have a look at that in the workshop. Because this is a real device, you can stick a screen on the front, connect it with HDMI, and you can just do web development on that device. If you can build a digital photo frame as a web page, then you can just run that on the Raspberry Pi and straight away have a nice photo frame. So I've got one set up that pulls photos from the Facebook API, lets you swipe back and forth between them, and attaches a motion sensor because you've got these GPIO pins, so why not use them? Using this, you can really easily move your web skills straight onto these devices. If you can build a web page, you can put that on a screen on top of a Raspberry Pi and build interesting goodies. Okay, you can also do things like electronic drum kits. You've got some interesting technology here. There's a hat actually from Pimoroni. Pimoroni.com are a quite good place to pick up lots of these interesting gadgets. And this is a hat that sits on top of a Raspberry Pi and comes with a bunch of sensors so that you can tap it and pick up touches on there. And you can use this to build little drum kits. Or even take this out further, take actual sensors and attach them to real pads and build an electronic drum kit all by yourself. Once you've got those inputs into a Pi, generating sound on the Pi is actually a pretty easy thing to do. And even more generally, you can just take the kind of projects you do with an Arduino, like plant waterers, and you can make them magically powerful. You can run them on 100 Raspberry Pis that stay in sync and water at the same time across your whole farm. You can set up a webcam so that you can check on your plant when you're away on holiday and concerned about its well-being. You can get a lot of extra functionality because of the stuff you have available here. Okay, so that's pretty much everything I have for you today. Let's just recap and go back through these. We've looked first at remote sensors. There's a lot of little tiny boards like the MetaWare that will allow you to build very simple things really easily on top of the hardware you already have. You can add remote sensing, remote action to your devices very easily using these tiny little platforms. We've also got microcontroller boards that allow you to get much closer to the hardware, allow you to directly control what's going on and really get started with electronics with no distractions. You can write voltages and see exactly what's going on with no other challenges around. And we've got full single board computers, things like the Raspberry Pi where you can do everything you would normally do on a computer, but in this totally autonomous, very small, portable form factor that you can move around, that you can stick to places, that you can do exciting things with in the real world. Again, there is a workshop today in the Taipei room at 3:15, so if you want to come and play around with it yourself, if you want to look at this, if you want to just try and work out how on earth these demos worked, because you couldn't really see them on the terrible screen, all of that you can come and do at 3:15 in the Taipei room. And if I can leave you with just a couple of things, I am Pim Terry on Twitter and everywhere else, and I will be putting the slides out on there in just a minute. So do have a look there if you want to take a closer look at those. And if there's one thing I'd sort of suggest you try and take away from this, it's that hardware is really not that difficult. In the course of the last hour, I've done maybe, 8 different demos of different interesting configurations built from scratch in front of you. You can do this too. None of the JavaScript here is wildly complicated. We're not doing anything enormously difficult. You can take the same JavaScript skills you have, a lot of the same web technologies and interesting things, and you can build these interesting devices all by yourself. You can get that same magic of programming back here on physical devices in the real world. Thank you. So I think we're a little bit out of time for questions, but I will be around, so just come up and talk to me if you want to ask about anything, or, of course, apparently there's a workshop.